And now, first of all, like I would like to thank our director of the campus, Dr. T.S.
This
Now,
conference will now be
if you
recorded.
see, if you see, this slide tells you the distribution of the proved reserves of oil from 1999 to 2009 to 2019. That is how it is varying between these 2 decades. So you can see that there is an increase into the production from 1919, to 1000, from 1277 in 1999 to 1733.9 to 2019. So you can see the production of the oil is increasing. Now these various colors, they are representing the various continents, but you can see the what does it mean if the production is increasing, the reserves are remaining less. So that means production is increasing. Why? Because the consumption is increasing, because the population is increasing. But if you go to the basic parameter, that is the global reserve to production ratio, we can conclude from this that the global reserve to production ratio, that is R by P ratio, has shown recently in 2019 that the oil reserve in 2019 accounted only for 50 years of current production. So this data has been taken from British Petroleum Statistical Reviews of World Energy 2020. Now let us have a story about the gas reserves of world. See, it is the same story here again, from going from 1999 to 2019. There is increase into the production from 132.8 to 198.8 trillion cubic meters. So same thing, the production is increasing. Why production is increasing? Because the demand is increasing. Now if the production is increasing, the definitely the reserves are decreasing. That means the gas reserves of the world, as per the global R by P ratio, that is the reserves to production ratio, has shown recently the gas reserves in 2019 accounted for only 49.8 years of current production. Now going to the same story about the coal, these this has shown that from 1999 to 2019, there is increase into the production, but still the R by P ratio here for the coal is bit favorable. Here the reserve to production ratio has shown the coal will provide us the source of energy for 132 years left. So you can see now this data is from the BP statistical reviews of 2020. Again I'm telling you, the BP statistical reviews of 2016 has given the age of oil as 50.7, which is consistent with the latest data. They have given the age of the natural gas with 52.8, which is again consistent. It is all 50 in 2009 and 52.8 actually in 2016. But if you can see, the age of the coal in 2015 was said to be 114, but in 2019, the same body, that is the statistical reviews of world energy by the British Petroleum, have given the age of 132. Why? Just because sometimes, because we are talking of only about the proven reserves, because at that time the unproven were more, because with the time maybe the technology has enhanced, so that is why the proven has increased. But you can conclude from these slides that this situation is alarming. You don't have you don't have much of the reserves left for more than a century. Actually only coal is left, other resources are half for a century. Now another issue which the last speaker, very learned professor, Dr. Sharma, was talking in two of his presentation. He was focused to move to the renewable one. Why he was focused to move to the renewable one? Because of the atmospheric CO2 uptake by the earth. So I have brought here on this slide by data by Mauna Loa Observatory in Hawaii. This data is showing you the latest uptake of CO2 by the earth within a gap of 1 year. On September 3, 2020, the CO2 uptake was 401.69 ppm, and on September 3, 2009, the earth uptake was taking uptake of CO2 as 408.75. So you can conclude from this slide there is an increment of 2.94 ppm, which is 0.72% increase within a year, which is a matter of very much it's a matter of very much worrying actually, that within a 1 year the earth has taken 0.72% of more ppm. So you can again say that all those kind of coal and oil, they are not in favor of burning because they are giving CO2. So we must now, come to another thing which is in favor of gas hydrates. That is what it is, that the natural gas, they emit 50 to 60% less of carbon dioxide when you combust in a new and efficient natural gas power plant, and when you compare with the typical coal plant. You can see, if you burn the natural gas, if you will burn the natural gas, you will get the minimum kg CO2 per kilowatt hour. If you compare with any of the resource, the natural gas is giving 0.20, and if you compare with even crude oil, if you compare with coal, that is peat, lignite, or any diesel or anything, the ratio is more than 0.2. So now, again data, another data which I am bringing in my favor to talk of gas hydrates for rest of 45 to 1 hour. Another data which is favoring my talk is that has been released by the International Energy Agency in Paris on November 12, 2019. So I've tried to show you the latest data actually. So they have said that the economic growth and the rising global population means that renewable energy source cannot keep with the worldwide energy demand. This they published in World Energy Outlook recently. Now you see this slide here. We are talking in 1919. Here we are talking of 2040. You can see, there is a markable shift. Here we are in 1999. We are maximum burning wood and coal, and then slowly in 1974 we are talking of, we are talking of oil. Then in 2000 we started talking of natural gas. In 2018 we are talking much of natural gas. We are reducing the burning of oil and coal just because the anthropological release of CO2, because it is an alarming situation at the moment. So you can see in 2040 there will be a remarkable shift on the gas based economy, on the gas based production, on the gas based vehicle transformation, because you can see the area of this sea green is increasing with time, and the area of this bluish area is decreasing with time. That means wood, coal and oil, the world is not favor of. We are in favor of talking of natural gas or some other renewable one. So outcome of the above talk is that the conventional fossil fuels are estimated to be depleted, and the rapid growth in energy demand, coupled with the worry of anthropological release of CO2 into the atmosphere, has seen growth in natural gas consumption, and depletion of conventional reservoirs of fossil fuel, and resulting rise in the price has led to the exploitation of new resources through modern technologies, and using every yardstick, that is availability, efficiency, environment, cost. The coming century will see an irrevocable shift towards gas-based economy. So with no major findings, gas reserves will be an interesting candidate to talk about, to see as a future candidate fuels. Now let us talk of now the going to the second point, that is about the basic fundamentals about gas hydrates. I have given you the justification that why we are moving to the gas hydrates. Gas hydrates are nothing. They are a methane hydrates. They are composed of methane. They are composed of natural gas, and they are crystalline compounds. They are formed of water and methane and maybe natural gas. Now, what happens? A water molecule forms a cage by hydrogen bonding, and those water molecules, they are called as host. And the methane molecules, they occupy the void spaces, and they are called guest. There is no chemical reaction. There is only a physical bonding. They occur actually into the sedimentary deposits in some permafrost regions, and they occur beneath the sea in other continental margins. If you talk of thermodynamically, hydrate formation, it is favored at very high pressure and at very low temperature. Now, if you what I'm talking in this slide, I'm again talking in this slide again. Here I was talking that water will make a hydrogen bonding, and it will be called as a host, and the methane will go inside this hydrogen bonded water, and it will occupy the some spaces, the void spaces, and this is how the methane hydrate cage will be generated. But let me tell you, there are three structures proven, that is structure 1, structure 2, and structure H, that we will talk of. As far as the methane is concerned, it forms structure 1 type of hydrate. If you talk of CO2, they again form structure 1 type of hydrate. If you talk of natural gas, they form structure 2 type of hydrates. But we'll talk of these structure in detail. Now, I told you there is no chemical reaction at all between the methane and the water molecules. The methane is there into the basins. Now, the methane can be either of biogenic or of thermogenic origin, or it can be a mixture of biogenic or thermogenic. Now, the methane clathrates are formed. How they are formed? This G, it is what? It is a gas molecule. This gas molecule will be the gas which will be going inside the host. For the timing, it is methane. It can be natural gas, it can be CO2, it can be anything. Now, this H2 is a H2O. It will form a hydrogen bonding, and NH is the maximum hydration number. So when the methane will go, it will form structure 1, and the value of hydration number is 5.71. This is the maximum one. This will lead to the complete hydration. If you talk of the types of structure, structure 1 and structure 2, they were discovered by Stackelberg, and structure H was discovered by Ripmaster. Structure 1 is cubic. Structure 1 consists of 2 small cages made up of 12 pentagonal surfaces called 512, and 6 large cages again of 12 pentagonal and 2 hexagonal surfaces called 512-6-2. Now, it contains 46 molecules per unit cell. Methane forms S1 type of structure, and the gases which are having the similar size like CO2, SO2, H2S, they also form structure 1 type of hydrate. Now, this is the representation of structure 1. I talked you there will be 2 small cavities of 512 type. There will be 6 large cavity of 512-6-2 type. This 512 is also known as pentagonal dodecahedron, and 512-6-2 is known as tetrahedron. If you talk of structure 2 is again a cubic. Structure 2 consists of 16 small cages. That means over here 2 was coming, now 16 will come. It's made up of again 12 pentagonal, that is again 512, then 8 large, again of 5 pentagonal, and 4 hexagonal, that means 512-6-4. It contains 136 water molecules per unit cell, and the higher hydrocarbons like ethane, propane, butane, they do form actually structure 2 type of hydrates. Now, it's a 6 small cages and 8 small cavities, 8 large cavities, 6 small of 512, 8 large of 512-6-4. This is pentagonal dodecahedron. This is called hecakite, dodecahedron. Structure H. It is a hexagonal crystal. It consists of 3 512 cavities, 2 small 435-6C3 cavities, 1 large 512-6-8 cavity, and it has 34 water molecules per unit cell. Cyclopentane in presence of methane forms the structure H. Actually, we are much interested into the number of water molecules. Once we'll talk of dissociation technologies, once we'll mature further into the topic, this number of molecules play a vital role. So over here, there will be persons of different background. Like I want to tell you is that this must be very much clear that the structure 1 has 46 water molecules, structure 2 has 136 water molecules, and structure 5 H has 34 water molecules. And these are the reasons. These are their unit cell looks like this. So these are the reasons why do they have this much water molecules? Because their lattices are like this only. This is 512-3, 512-6-2-1, 4-3, 5-6-6-2-2 cavities. Now, coming to the again few more fundamentals before going to the energy potentials. The one volume of gas hydrates, it can release about 160 volumes of methane at standard temperature and pressure. It's a big thing. What I'm writing is that if you have one volume of gas hydrate, it can give you 160 volumes of methane. So imagine the kind of gas that is tapped into the hydrates. So it has a tremendous reserves of natural methane in the earth. Their observed density is around 0.9 gram per meter cube. They are found naturally in the areas where methane and water, they can combine automatically under a high conditions of pressure and low conditions of temperature. So what does it mean? If you are having anything into the nature which is having high pressure and low temperature, definitely the hydrate formation will take place. Now, coming to the next thing, why should we look them as energy candidate is because whatever the carbon which is contained into them, it is roughly around 10,000 into 10 to the power 15 grams, which is almost double the content which is there into the all the fossil fuels which have run for so many centuries, that is crude oil, natural gas and coal. That too of both sides, that is recoverable and non-recoverable. That means the total carbon contained into the fossil fuels, that is combo of recoverable and non-recoverable, is half of the carbon which is there into the hydrates. So making them future energy, prominent future energy candidates. So that is why they need our immediate attention. Now, if you talk of occurrence, this has been again told that they'll be definitely start forming where they'll be getting a condition in nature of high pressure and low temperature. If you talk of they're globally present, here I'm talking, if you talk of, there are two type of circles. The red one are the inferred one and yellow one are the known one. So yellow one are the one which are definitely, they have passed all the signatures, they are definitely there, and the the red one are the one which have passed few signatures, like seismic data they have passed, but there are few techniques they are still going through, but they are expected. It is expected that they are the resources of hydrates, but it is expected. But the yellow one are the proven one. Now, if you talk of worldwide, they are scattered in the Gulf of Mexico. They are there into the Japan. They are there into the Peru. They are there into the Eastern Trench. So they are there worldwide. They are having their signature from the Southern America to the even going to the North America. They are having their signatures. Let's talk of India now. Into the Indian context, the richest gas hydrate deposits, they are 130-meter thick. They are into the KG basin, and the thickest one is 260 to 600 meter. It is into the Andaman. So you can see in my coming next slide, we'll again tell you the quantum. The quantum, India is having the is leading amongst the quantum. So they are present again in India, in KG basin, in KK basin, in Andaman, and they are formed uh, again that whenever they'll get conditions of high temperature and low pressure, they'll get formed. Now, if you talk of their historical perspectives, period one was they were just treated as a curiosity of laboratory. There's nothing more than that, only they were a lab curiosity, like so many compounds we are just experimenting into the laboratory, and they were just tried as a laboratory curiosity, nothing more than that. But period two was not favorable for the hydrate. They were recognized as a nuisance to the natural gas and oil industry. Actually, it was seen that many oil and gas pipelines, they are bursting, and the reason which was found after the investigation was the formation of hydrates into those pipelines. So period 2 was a when in the history hydrates were found not as an energy candidates, they were found as a nuisance to the industry, and millions of dollars and lakhs of rupees the industry even today spends in order to inhibit their formation. Now, period 3 was very much favorable. After this, they were found into the nature as such, into where I have shown you they are given their signature worldwide into different basins. In period 2, they were only found into the pipelines, and pipelines were bursting because of them. So period 3 was a favorable for them because they were found as a energy candidate. If you talk of the classification, they can be classified in terms of their geological structure and in terms of their thermodynamic conditions. They're very much important. Now, they can be classified actually into 3 types. Class 1, these hydrates are made up of 2 layers, that is the hydrate layer, and underlying they are having, they are having fluid zone containing free gas and liquid water. I'll show you. That means this is a gas hydrate. Under that, you're having gas and water. In class 2, you're having hydrate, but under the water, there is absence of gas. That means class 2, they're made up of 2 zones. That is the hydrate layer overlying the zone of mobile water. That is class 2. Class 3, absence of any kind of mobile zone. It is only hydrate. You don't have any sort of neither water nor gas nor gas water, nothing. So they are this is a single zone of hydrate characterized by absence of any underlying zone of mobile fluid. Now, if you talk of, because this is very this slide is very heart and brain actually of my talk. So I'm just adjusting to show you. I'll keep on adjusting. Here I'm telling you, let's talk of India first. We are talking about gas hydrates in trillion cubic meter, and then we are talking about their usage year. If you talk of India, the gas hydrates are minimum one, which have given which is sure, that is around 1894. It can go up to 14,572 trillion cubic meter. Now if you see that if you see if you see, just a minute, if you see, you know if you see, yes, now I'm happy. If you see, because actually this is taking the energy potential. If you see, India can be energy free from 34,689 to 2,66,886 years if we are able to tap this resource of energy. So imagine, when we were talking of the conventional one, we were talking of one, that is the coal only, which is talking of more than a century. Oil and gas are left for less than a century, depending upon the R by P ratio. If we are able to tap, then we can, India can be energy free for so much year of usage. If you talk of word, the last one is showing a word actually. The last one is showing a word. That's what I'm showing word. Last one is showing for word. Word is having, this is this much trillion cubic meter, and word can be energy free for 6,134 years of usage can be energy free. So that means we should really talk of them as a serious candidate. Otherwise, all the data of all other country, from US to Canada, from Japan, Japan is not having very much you know quantum, and usage here will be less, but they are very much interested in this field actually. So this is China. This 107.7 is for China. So I mean, all other countries are also having the gas hydrates, but the Indian one, the another beauty about the Indian gas hydrates is that they are very much exploitable actually. Now, now this data I have taken from the Ministry of New and Renewable Energy from Government of India, published in the report on 31st of December 2019. They are saying that they can produce collectively somewhere around 7,000, total quantity was somewhere around 7,000 megawatt. So independent, if you talk of wind power has stopped, then followed by the solar power, and the last is the waste to the energy. So that means it can, by 2019 it has given around 7,000 megawatt despite of so many efforts into the renewable one. But let me tell you, if we are able to, if we are able to, you know, if we are able to tap the minimum one, that is 1894, it can give you lakhs of megawatt. Because if you will convert 18 trillion cubic meter into megawatt, you'll get to know, you get lakhs of megawatt. So you can see that, that means they need our attention actually. That means they can really replace all the other players which are being talked, and they are not the kind of the scenario for gas hydrates is there at the moment. If it matches with other renewable one, then probably the story will be different. Now, if you talk of USA, they have released data recently. They are saying that if they are able to tap only the 1% of methane stored in these hydrates, if they can recover somehow, it would be double than the current domestic supply of natural gas currently they are using at the moment. So we can say them from these slides above, they are recognized as future potential energy resource based on the vast quantum of methane tapped in them. They are considerable because of their potential quantum. They are considerable because they are potential energy resource because of the quantum in them. uh, the energy potential of methane hydrate is greater than other conventional source, such we are talking of coal bed methane, we are talking of coal beds, we are talking of even the conventional natural gas. So their energy potentials are maximum, and their occurrence globally suggests that they will be the future candidates for the energy. Now, despite of having so many advantages, only for a moment we'll talk of, they're having only one disadvantage, that whenever they do the plugging of oil and gas pipeline, whenever the oil and gas they flow, gas hydrate formation takes place. For that, the oil and gas industry, they do take care of that they don't get formed. If they get formed, so this is the kind of growth that of hydrate which takes place. So then there will be two parts in the pipeline with the pressure difference. So then there could be some blast which will be not good for the equipment and human. So this is the one disadvantage the gas hydrates are having. So that's again which I have told you, they do block the pipelines and putting a considerable economic threats. But a lot of research is going in petroleum industry to avoid their occurrence. And because some plug is formed and it divides the pipe into two sections that is of different pressure, and because of them the blast can happen, putting the danger for human life and production equipment. Now coming to the another target which we have fixed, that is about, we have talked of need, we have talked of the energy potential. Now the talk is that how to extract the gas from natural gas hydrates. That is that is what the uh, that is what the most important part is. If you talk, if before starting these techniques, I must tell you, currently as of now, currently we don't have any technology at hand actually to exploit the gas. We don't have Currently we don't have any kind of technology to extract this reserve. Still we are trying our best to design some technology, but still we don't have. But still we can try depressurization, we can try thermal stimulation, we can try inhibitor injection, we can go for CO2 sequestration. Among them, depressurization and thermal stimulation are considered to be quite economical. And now what sort of method you will apply, that depends upon the characteristic of the reservoirs actually. And if you talk of depressurization, we'll start taking one by one. This is an extraction technique involving a drilling of the hole into the layer of the hydrate. This will reduce the pressure beneath the hydrate equilibrium and it will incorporate an endothermic reaction, and that will help in absorbing the heat from the reservoir. It will result into the release of methane gas from the hydrate flowing up the pipe, and this dissociation will prevail until the equilibrium is maintained at this lower temperature. This has advantage because it is very much economical and it is quite less energy intensive. You can see over here, it seems very simple science that you need to reduce the pressure and the gas will start coming, but it is a very complicated engineering, and we don't have any kind of technology which can dissociate them, but it looks that it is very simple science, that here you are. But the another condition which this hydrate the dissociation by depressurization will be applicable to those zones where which are having free gas beneath. Then and only then you can apply the dissociation by depressurization. uh, where I have told you that where the free gas is found, then and only then you can apply. Now, because of the increased heat exchange, the reservoir zone temperature falls below to the equilibrium level. What happens actually, because heat exchange is occurring, the reservoir temperature will fall down. If it will fall down, again the hydrate formation will take place, because the lower temperature and the higher pressure favors the hydrate formation. You have decreased the pressure by depressurization, that has started taking the temperature from the reservoir. But then what will happen after some time? The temperature will drop because it is giving the heat actually. So if it will drop, the hydrate formation conditions will arise. So that means it is not a very viable solution. So the viable solution lies in inventing a technology which can dissociate them continuously into the porous medium. The second one, the second one is the inhibitor injection. It is nothing. It is only you inhibit the formation. This is being followed by the gas pipelines. They do also follow this. They put certain kind of inhibitor that the hydrate formation doesn't take place. So the chemical inhibitor like methanol, what do they do? They reduce the dissociation temperature. So if the dissociation temperature is reduced, so that will help in taking the hydrate from their hydrate stability zone, and the hydrate will be coming out of its stability zone, and then the hydrate will start decomposing. For this matter, you can have either organic inhibitor like methanol, monoethylene, diethylene glycol. You can even use some salts also like NaCl, CaCl, 2KCl, NaBr. It's like a simple technology where if you live in into some European countries where the people are putting salts on the roads, in order to melt the ice. So the schematic representation is that you will be putting methanol. It will be going to the hydrate zone, disturbing the equilibrium. The impermeable rock is there down, and impermeable rock is there on the up, and the hydrate will dissociate the gas, and the gas will start coming. But the demand which is being put by this method is, the demand which is being put by this method is that ample of porosity this method demands. This method demands that the porosity of the reservoir should be very high, and very sound and you can use even salt brines, you can use glycol, etc., which we have already talked. Now coming to the next technique, that is about the thermal stimulation. It is the extraction of gas from the reservoir using some steam injection or some hot brine solution. What it will do? It will do nothing. It will just raise the temperature of the local reservoir. If the temperature is risen, the hydrate will again come out of its stability zone. It will because it is only while the initial slides was taught that the hydrate formation of possible or stable at higher pressure, lower temperature. So you have risen the temperature, it will come out of its stability zone, it will start dissociating, and what will happen? The methane gas, it will mix with the hot water, it will return to the surface where the gas and hot water are separated. Steam and hot water again can be pumped, and it can be used again, for the dissociation. And solution carries heat to the hydrate zone, and the dissolved salt, what they do, they lower the dissociation temperature. So it is a win-win kind of situation actually. If you say this diagram over here, what we are doing, we are putting steam or hot water, and the hydrate, hydrate is getting unstable, and the gas will start coming out because the temperature has risen, and the formation of hydrate is not will be dissociated, just because the now it is stable at a particular temperature, at a particular pressure. you know Now, the efficiency of this method is directly proportional to the latent heat of the brine which you are sending, the rate at which it is injected, and the what is the saturation of the hydrate initially. That means how much quantum of gas is there inside the reservoir. Now, although commercially we have no viable technology, having very simple science, but we don't have any kind of technology at the moment. But still, using certain kind of modeling and economics, it has been predicted into the literature. This data I have taken from literature, that if somehow this method becomes tomorrow, the taking energy from hydrate becomes a reality, then maybe thermal stimulation, will be not cheaper than the depressurization. You can see that if you compare the investment cost in terms of millions of rupees is higher. It is a very you know very investment kind of field, and then annual cost is again higher, production cost is again higher. So if we compare the thermal stimulation with depressurization, this technique favors in terms of economy. If we compare other advantages and disadvantages, thermal stimulation has poor efficiency. It disturbs the hydraulic and mechanical properties of the reservoir. If you talk of the depressurization, it requires heat transfer from the surrounding environment, and it also disturbs the mechanical stability of the reservoir. You know, then if you if you talk of the another CO2 sequestration, which I have not talked at the moment, I'll be talking. It has low efficiency, but still a very novel technique actually. We are going to talk of now the CO2 sequestration, which is under investigation. Maybe with time, if hydrates become a reality tomorrow, CO2 sequestration will be one of the vital technique. Yes, it's nothing. It's a very simple gas exchange process which enjoys the greatest stability of CO2 in water to displace the natural gas or methane. So now it is going to solve your two purposes. One is this, that you will be extracting the natural gas from the gas hydrate, and second is this, you will be removing the CO2 from the atmosphere. That means you will be getting the energy resource at the expense of reducing the global warming, because CO2 will be going inside the sinks. So this was first studied actually in the lab. You can see here the hydrate formation is a endothermic process. So whenever hydrate will be formed, actually heat will be released. So once you will send CO2 into the reservoir, what will happen actually? This much heat will be released. So what the other techniques were doing, the thermal stimulation, what those things, the steam, everything, they were dissociating via giving a heat of, if you want to dissociate the methane hydrate, 54.49 kilojoules per mole is required. But if you put CO2, it automatically gives 57.98, which is more than 54.94. So automatically what will happen, the hydrate of CO2 in this layer of the basin will get formed, and methane will start coming out of the basin. So that means you will be solving two problems in a one go, and both of them form structure 1, but the efficiency of this process, that is why they are compatible. CO2 and methane, they form structure 1 actually, and the efficiency of this process still needs investigation. I mean, these are long-term plans. Actually, nothing is there at hand on now. We are just trying, and nothing at hand there into at any at world level. But still, it is being talked of actually that one day probably CO2 will go inside sea and you'll get the electricity at your home. It is just a proposed model only that CO2 will generate methane. It will go to turbine. It will go to transfer, and then it will go to the grid, and from grid it will come to your homes. But it is just a hypothesis only. Now, I told you that if you need to increase the efficiency of the hydrate formation, you can always use a surfactant along with. What I told you that the CO2 sequestration is a low efficient process. There are many methods actually which are being tried. One method to, in general, to increase any hydrate formation, be it of CO2, be it of any hydrate, is you may is that the form the hydrate in presence of surfactant. What they will do, they will act as a catalyst. They will put a catalytic effect on the hydrate formation because they will form a micelle actually. The 12 carbon alkyl group, they will form a micelle, and that will solubilize the hydrocarbon gas. Now this water, because that water has to role to play. Ultimately, this water will be forming the cavities. It is the host, getting my point. These are the gases, the guest actually. So this water will associate around this periphery of this micelle, and in the proximity of this solubilized gas. I mean to say, you can understand it like this: this micelle is going to act as a nucleation for the crystal growth of the hydrate. Moreover, they tend to promote the hydrate formation at the interface by lowering the surface interfacial surface tension at water gas interface. Thus, they facilitate the transport of gas in contact with water. Thus, studies reveal that micelle act as a nucleation point by increasing the solubility of hydrocarbon gas in the aqueous phase and by inducing the formation of hydrate crystal around the micelle. So that means if you want to increase the formation of hydrate, so you can always use surfactant. Now, what is influence actually? What is the influence on environment of the use of this energy source? You know, the latest research it's going on, which I have talked of, that our model that we have really talked, we have shown you that going CO2 inside, coming methane out. So if that becomes tomorrow reality, then the exploitation of this resource, this vast resource rather, I must say, will happen through the CO2 sequestration. That means you will obtain the energy by dumping CO2 into the sea, and you'll be reducing the global warming. Now, but that is not that simple. It's not that simple because there are so many threats. Many scientists are working on many areas, whether to go for commercialization or whether not to go for commercialization. And if we need to go, how should we go for the commercialization? First of all, though, we don't have any economic viable technique. If at all tomorrow it will come, it will be a subject of a lot of policy makers will be there. Actually, what is the reason is there is a threat actually, because the controlled release of methane from the gas hydrates while CO2 sequestration is a threat, because what will happen if it will be dissociated in an uncontrolled manner? Imagine the methane coming from the gas hydrates at such a quantum. I shall show you the quantum, show you how much million cubic meters. If that much methane will reach the atmosphere, so you can imagine Earth is not a suitable place to live. But however, the scientists who are working in this area, they have said that the CO2 sequestration is into the favor. They are saying whenever it will be, this event will happen, if at all this will happen, whenever CO2 will go and methane will come, and methane will start coming at an uncontrolled rate and not a sustainable, at an unsustainable rate, it will be converted to CO2, before reaching to the atmosphere. That means it will not come as a methane. Before even coming to the atmosphere, it will be converted to CO2, which will be sequestered. I mean, the biosphere, the hydrosphere, they will take that CO2, And again, that's CO2. Again, this should be the question. It will not go to the hydrate, because it will go again to the hydrate, then again methane will be released. No, no, that if at all this event happens, the scientists are saying that it will not reach to the atmosphere, it will convert to CO2, and that CO2 will be taken by the biosphere and hydrosphere, and it will not go to the hydrate again. That means again methane will not be released if this event happens. Now going to the favor, as far as the environmental issues, because since the morning we are talking about that we need to talk of the CO2 load on the earth. So if you talk of the combustion of methane, it generates lesser CO2 in comparison to if same amount of coal or oil is burned. So the amount of CO2 generated will be quite less, you know and let me tell you, it is also not generating NOx and SOx also, which makes it more environment friendly. What are challenges in front
Right.
of gas hydrates? Challenges in front of gas hydrates. There are many challenges in front of gas hydrates. It's not that easy that you need to only put and go the drilling, put the steam, put the CO2 and can get the methane out. Not that simple. You see, the release of methane gas hydrates and seabed geological disaster. It may happen so. The geologists are studying hydrates from this angle. They are not studying hydrates from the angle of energy. They are studying from this angle. If tomorrow the hydrate becomes a reality, which is really expected, because at the moment we don't need, because coal is left, the many things are left, so we are not taking them, we are not giving them a serious call. But if tomorrow we need to definitely go for the commercial production. So the geologists are saying they are working, they are inventing their technologies, that whenever actually what happens, these accumulation of gas hydrates are not the same accumulation like the conventional one, like coal, oil and natural gas. Actually these marine gas hydrates, they are prone to phase transformation. What does it mean? The sometimes hydrate is also called as SNG, that is solidified natural gas. So whenever hydrate will dissociate, at that time, the phase transformation will occur. So what is then what the geologists are saying? They are saying that the submarine sediments, they will move downward under the action of gravity. It can lead to landslide, and you may have to face certain events of tsunami, etc. But still geologists are working in this direction, and we have sufficient time, because as of now we don't have any technology at hand to go for the commercial production. By the time maybe these calls will be also answered. Then is the greenhouse effect rapidly, which I have already talked. If while for commercial production, there occurs a technological failure, instead of controlled and sustained release, the methane starts coming out in an uncontrolled manner, then in that case there will be a complete disaster through global warming. So in that case, Earth won't be suitable for living even. Then another scientist, those who are ecologists, they are having their own worries. Actually they are saying that there is a biostrata, there is a life actually, which is dependent on the submarine life actually, that is dependent on the gas hydrates. They do say that if we will go for their commercial production at a one for go, and they say that if supposingly if you try a technology and you are not able to control somehow, and they start dissociating in an uncontrolled manner, there will be distinction of so many species which are dependent upon them under the sea. So that means it can lead to their extinction. That can really disturb the food web, it can disturb the food chain, because lot of submarine life is dependent as energy resource on these hydrates. So there are many sciences are having their own worries. So investigations are going on before we go for any commercial productions. Maybe we'll be in a position to answer such calls. Now the development and utilization of this new energy vast resource, it must be based on the premises of safety development. That is the first issue, that the premise should be on to the safety development, we'll go definitely. Maybe we'll go after some time, with a great amount of time, but definitely whenever we'll be going for the mass production, we'll be definitely taking safety into consideration, whether tsunami should not come, ecology should not disturb, global warming should not happen, because we are doing it for what purpose? We are not using bio we are taking it as a replica of biomass. Why? Because of the CO2 issue. But if supposing if safety won't be an issue, it will, instead of controlling the global warming, it will cause the global warming. And environment, safety has to be taken care of. So the any production technology which will be going for the commercial viability has to prove its safety first. And you know at present, if you talk of at present scenario, the development as well as the utilization of this vast resource of energy are still tentative. So in order to use this energy, we must consider ways to protect the biodiversity as well as the marine ecosystem on priority basis. Coming to the conclusions of today's talk, you know, the first conclusion is that enormous amount of methane is available in gas hydrates, which has been discussed. Now, they are present worldwide. That is why every country is putting an interest. In few countries, they are into the bottom of oceans. In few countries, they are in some permafrost regions. As far as the amount of gas hydrate is concerned, no other resource can match this upcoming resource of energy. That's why they are seen as future energy fuels. Moreover, they are clean energy source also, because they will be definitely giving you methane, and few structures may give you natural gas, so they are considered as clean because they generate less CO2, and moreover, if they don't generate SOx NOx also. Now, the small amount of percentage can meet the energy requirements of world for centuries. Furthermore, we would also be able to elevate the problem of worldwide climate change that has been troubling mankind for a long time, as CO2 released will be significantly reduced if they become a reality. And definitely, if our model which we are talking about, if that becomes a reality, then CO2 will be dumped also into the sea. So if we start exploiting the methane that is captured into the natural gas hydrates, the problem of this global warming can come to a rest. If exploited properly, they will be the next generation energy resource. There is an urgent need for finding economical, viable methodology for exploiting this vast energy untapped resource. Sequestration is one, CO2 sequestration is one such technology which can take the energy from this source and can reduce the global warming side by side, sinking CO2 into the gas hydrates. Global efforts are being put in the field of gas hydrates by various countries like USA, Germany, China, India, and they've joined hands together and they are doing programs together for the exploitation of this vast source of energy. Long-term production tests are planned in USA and in Japan to establish the viability of production technologies, because we as of now we don't have any economical one, and if at all we'll have one economical one, you know it will have to go for the testing, and many issues which I have talked, it has to address, then only then taking energy from this fiery ice will be reality. However, if we try and exploit the methane that is entrapped into the natural gas hydrate, it would guarantee that we have an adequate energy resource in the world for future generations and future of the mankind. It is expected that the dream of taking energy from fire in the ice will be reality very, very soon. However, there is a strong need to prepare a suitable green technology for taking energy from this un, un tapped resource, vast resource of energy. So you know uh, you see, uh, like I try to present whatever, like you know starting from the fundamentals to the techniques, and this is this is about my presentation. And yes, if any, these are the references. These are the references actually which I have referred, and yes, sir.
So thank you, Dr. Amit Arora. From the
Thank you,
participants,
sir.
if you have any questions, you can ask. Otherwise, I have some questions through WhatsApp which I have got, so I will ask later. So, Dr. Amit, please uh, tell whether this energy extraction from this gas hydrates will be a reality. Is it there are there any chances of such extraction or?
Rajiv sir, let me thank you for asking. It's a very meaningful and very much significant question in related to my research. Actually, sir, still there is a still this question. I mean, needs lot of explore. It needs to be explored actually. Although like within some time we may have some technology actually ready, for the production of energy from the gas hydrates, but there it has to pass through from many angles. It has to pass through from the angles of geologists, it has to pass through from the angle of environmentalists, it has to pass through from the angle of biologists. So that means we can definitely at the lab scale or at the pilot plant scale, we can definitely design, and we are designing, and probably the world will have this technology at the lab scale. But at the commercial scale, sir, it is still a question which needs a lot of discussion and lot of involvement of policy makers. But what I perceive is that probably when these resources of oil and coal, they will start depleting, maybe at that time, whatever the technologies, which will be ready by that time, maybe at that time the policy makers, they may, allow us, and they may think of the commercial production. But as of now, in the near future, it seems it will be it seems not realistic actually, because lot of they are saying that it can bring tsunami, they are saying that it can disturb the ecosystem. So maybe when the time will come and the price will when we don't have any choice actually, then maybe at that time some commercial technology will be tried. This is what my perception is.
And is there any technique for taking energy from them right now?
Yes, sir. As of now, the depressurization has been tried, but it was not successful actually, sir. But it is expected that maybe with some time CO2 sequestration will be tried. But as of now, actually, we don't have a full signature technology which can surely give you gas, at a continuous rate, because sometimes gas comes, but then because of some problems at the seabed, because of the porosity and because of certain disturbances, the operations becomes not successful. So these are under study, but still it seems that with passage of time, CO2 sequestration will be an answer. Why? Because the depressurization and thermal stimulation, they disturb the reservoir. In CO2 sequestration, the hydrate will not be disturbed. Only the hydrate of CO2 will be formed and the gas will come out. So, but still, sir, it will take some few amount of time. But maybe they are going to, Japanese people, they are going to try within few, maybe within 5 6 years, maybe they'll try this.
And where are the major researches going on in this field in India, apart from your team working
Sir,
on that?
actually, sir, in India, one team is carrying in NCL, National Chemical Laboratory, and few people are they are working actually at IIT Kharagpur. And sir, the thing is this, that most of them they are focusing on the mathematical one, because it is very difficult to go for the experimental aspects. So IIT Roorkee will be is in a position, like probably they'll be developing a lab. So with some time probably they'll start the experimental.
So, any other question from the audience participants? So, one question is how gas hydrates stored. It is from the this chat. Dr. Arora, can you please?
Yes, sir.
Someone has written how gas hydrates stored. This is
You
through
know,
our, yeah.
yes, yes, sir. Actually, if you need to store the gas hydrates, you cannot store the gas hydrates at the room temperature. If sometimes we need to go for NMR, sometimes we need to go for some another kind of technique, which is required for certain kind of signature. So at that time you need to store the sample for some time. So at that time, you need to have some, cryogenic kind of techniques actually, where they can have maintain the high pressure and low temperature. But you can, the moment it will come to the atmosphere pressure, they'll start dissociating actually. So you cannot store it at atmospheric pressure and at atmospheric temperature. There are special designed cryogenic kind of systems which can sustain them at a higher pressure and lower temperature. That is the only technique where they are stable.
Okay, sir. Thank you very much. It was a very wonderful presentation, totally new for all of us. And